Okay, we're going live. No swear words this time. Okay, section 1.5. Notice we skip. If you have your book and you look in your book, we're skipping section 1.4 of your book. Okay, it's actually lesson 1. Yeah, lesson 1.4 is 1.4 on the thing, but we're skipping section 1.4 in your textbook. We do not do parametric equations in here. That is a calculus BC problem. I love parametric equations due to time constraints, due to unnecessary not needing to cover them for this course, because they're not part of what's required for it. We don't do it. Parametric equations are really cool. You have your x and y coordinates are not based on each other. They're based on a third variable, usually time. X and y both change with time, not with each other. So you get some really gnarly stuff with parametric equations, but we don't do those in here. So a function is 1-to-1 on a domain D if f of A does not equal f of B, wherever A doesn't equal B. Okay, so this is a typical definition that you're going to have, and you're going to need to know and understand these definitions. Sometimes the definitions and theorems, you need to really understand where they come from. You may actually have to spit back parts of those. But with 1-to-1 on a domain D, that means we have a specific domain that we're talking about. Whether the domain of that function is all real numbers, whether we use the actual domain of the function, or if we limit the domain by constraints that we can impose upon them. But on any particular domain, if f of A does not equal B, f of B, wherever A doesn't equal B. So what that says is, whenever I have two different x outputs, I need to have two different y outputs. Two x's cannot have the same y for a 1-to-1 function. For a regular function, that's okay. But for a function to be 1-to-1, this is a subgroup of functions. These are functions that are 1-to-1. Okay. The horizontal line test is the easiest way to look at a graph and tell whether it's 1-to-1, and it also explains it quite well. If I pass a horizontal line through this graph, I have two x coordinates, this one here and this one here, A and B, that have the same y coordinate. It's not 1-to-1. Two x coordinates have the same y coordinate. It is not 1-to-1. It fails the horizontal line test. Okay, yes? No. It has to be a function to be 1-to-1. So a relation that is not a function is not going to be 1-to-1 at all. Because, yeah, it won't work that way. I don't think, off the top of my head. Because it has to be a function. Yeah, it has to be a function to begin with. It has to be a function. So it has to meet the rules of being a function. And you can see the second one does pass the horizontal line test. Every x has a unique y to go with it. And that's the point. Every x has a unique y. Okay. So example number 1, determine if the following functions are 1-to-1 or not by graphing them and using the horizontal line test. You need to understand what basic graphs look like. You don't have to have perfect detail every time. Okay? You don't have to have perfect detail every time, but you do have to have a good idea what they look like, and you have to be able to sketch a basic graph. Now lines, come on. You should be able to do a line, xy coordinate, and I'll put the xy coordinate on here. And 3x plus 2, which means it crosses above the x-axis and has some sort of a slope. I don't know if that's exactly 3 or not. I don't care. It's close enough for what we're doing in here. I don't have values placed on the line on my x and y coordinates, so I don't know for sure. I'm not graphing on a grid. I don't know for sure. This is close enough for what we need to do. Will that pass the horizontal line test? Yeah. Straight lines, except for horizontal. Yes, except for horizontal lines, pass the horizontal line test. Okay. So this would be 1 to 1. Did anybody graph this to see what the quartic one looks like? Horsepower. I can tell you it's not 1 to 1 just by looking at it. Okay. Polynomials. Here's a rule of polynomials. If your highest power is even, then both ends either go up. If the first term is, if the highest power has a positive coefficient, both ends go down if it has a negative coefficient. If it's an odd power, it looks like this. One end goes up, one end goes down. If both ends go the same direction, it is going to fail the horizontal line test at some point. It will. If that looks like either a parabola or a W. Fourth power is either going to look like a parabola or like a W. Either way, it's going to fail the horizontal line test. Now, I've got a pretty good idea. This one's going to look pretty much like a big fat parabola, or actually a skinny one, but it will fail the horizontal line test. But you should have some idea when you look at a polynomial, okay, is it going like this? Is it going like this? Or is it doing this disco thing? Okay, are we doing the YMCA? Or are we getting down the same line? Okay. You need to know basics. Not the squiggly crap in the middle, but you got to know what the basic shape is. You want the squiggly stuff in the middle? You want more detail? Graph it on a calculator or on a computer. Okay? But you should know the basics of what it's going to look like. Okay, does that make sense? But by all means, you can, anytime you need to graph something or want to picture what it looks like, feel free to use your calculator, use your Desmos on your phone or whatever. I don't care. Just remember, you won't be able to use certain things at certain times depending upon what we're doing on the test. Okay, and on the AP test the same way. Okay. Why do we need to know if a function is 1 to 1? It is important to know whether it's 1 to 1 or not because it has an inverse function if it is 1 to 1. If it's not 1 to 1, there is no inverse. If it is 1 to 1, there is an inverse function. It is extremely important. Okay. It's very, very, very important to understand whether or not something has an inverse. Because you can do things with inverse functions you cannot do with non-inverse functions. Okay. For one thing, you can use them to solve equations. If it's got an inverse, you can solve an equation by doing the opposite, right? Because that's how you solve an equation. Instead of adding 3 to both sides to get x by itself, you subtract 3. You do the opposite. You do the inverse. Inverse of addition is subtraction. Squaring and square rooting. Okay. Squaring and square rooting have issues because it's not 1 to 1. Squares are not 1 to 1 functions. Square root y equals the square root of x. If we're only counting the positive part is, but if we're counting both the positive and negative is not. So you have to be careful when you do that. But cube roots are 1 to 1. You take the cube root of a number, you're fine. You've done the inverse. Okay. The reason we can solve logarithms and exponentials using logarithms and exponentials, and I'm getting out of myself here, is because they're inverse functions. Okay. It's kind of hard to read this here, but the notation for inverse is f to the negative 1. That is inverse notation. Okay. You've seen that inverse notation before. Inverse trig functions. The only time something raised to the negative 1 is not 1 over that object is when you have the notation like this or in trig notation. Now, when I was a kid, I do not remember using sine to the negative 1 of x as inverse notation. When I was a kid, when I was your age, it was arc sine. Actually, when you take the AP test, they'll say arc sine is the same thing as the inverse sine. Our calculators didn't have sine to the negative 1 power. When I was a kid, sine to the negative 1 meant 1 over the sine. I don't know why it changed. Because it's confusing. but we will do inverse functions. And we're going to have a lot of F notation in here, a lot of F notation, a lot of G of X, H of X, a lot of stuff. You got to get comfortable with that. Make sure you're very comfortable. A lot of calculus notation using this. Questions? Okay. Finding the inverse function. Okay. And when you do your homework today, read carefully because some of the problems ask you, is there an inverse? Some of the problems ask you to find the inverse. There are two different sets of problems. Okay. Usually you can find an inverse. There are functions that are one-to-one that do have inverses that are extremely difficult to find the inverse function. I will never give you one of those. Okay. So as an example, we're going to show that, basically show that y equals negative 2x plus 4 is one-to-one. Is it straight lines other than y equals some number are one-to-one? And find its inverse. Finding its inverse really is not difficult. Okay. First step: solve the equation y equals f of x for x in terms of y. So I take my original function y equals negative 2x plus 4. Solve that equation for x. Subtract 4, not add 4. Subtract 4 from each side. Y minus 4 is equal to negative 2x. Divide by negative 2. And y minus 4 over negative 2 is equal to x. Now to find the inverse function, swap the x and y. That's the inverse. This is the inverse of that. That's what you do. Take the one equation, solve it for x in terms of y, go from there. Sometimes an inverse will exist, but doing the algebra to find the inverse is nigh on impossible. I will never ask you to do something like that. The ones I ask you to do are ones that you can do. Okay, and they're usually pretty simple. There are a couple little tricky things. Questions so far? Okay. So if two functions f and g are inverses, and I know it's spelled wrong, I tried to fix it this morning and I couldn't get it to open up right so I could fix the misspelling on inverses. Drove me nuts. Then f composed of g of x equals g composed of f of x, which equals x. So if I have two functions and I take the composite one way and I take the composite functions the other way and I get x for both of them, then the two functions are inverses. So let's say, for example, I want to take what I just worked with and prove that they're inverse functions. I will go f of x was negative 2x plus 4, and g of x is x plus 4, or is it x minus 4? X minus 4? X minus 4 over negative 2. Thank you. Minus 4 over negative 2. And I wish to prove, I wish to prove that these two functions are inverse functions. Two conditions must, well, I need to prove, to do that, I need to take the composite, show that it's equal to x. So I'll do the first one. F composed of g of x. So that's negative 2 of x minus 4 over negative 2 plus 4. So f composed of g of x. Negative 2 times that, I get x minus 4 plus 4. F composed of g of x is x. Am I done? No, because it says both of them. It's extremely rare that only one does and the other direction it doesn't. But if you don't check, you're not doing enough. Okay? You're only going halfway. You got to go all the way. So you do it again. G composed of f of x is equal to negative 2x plus 4 minus 4 over negative 2. G composed of f of x is negative 2x over negative 2. G composed of f of x equals x. They're both equal to x, which means they're equal to each other. My condition has been met. Therefore, f and g are inverse functions. Three little dots. Therefore, we'd rather put 3 little circles than write out an 8-letter word. Okay? Questions about this? To prove the two functions are inverses, this is what you do. And yes, you have to do both. Because it is entirely possible that it does only work one direction but not the other. It's rare, but it is possible. Okay. And the next slide, please. Okay, the inverse of the exponential function y equals a to the x is the logarithmic function y equals log base. It should be log base a of x. Sorry, typo, my bad. I gotta fix that. So I have an example here of y equals e to the x, y equals the natural log of x. Those are inverse functions. That's why I use one to solve the other and vice versa. Okay. And I have them displayed up here graphically to talk a little bit about inverse functions. As you remember, so as you may recall, the line y equals x is the line of reflection for inverse functions. If I were to take that graph, take the screen and use my super strength and fold it over, and crease it perfectly right on there, the two graphs would line up. Okay, that's part of an inverse function. If you can do that, they line up their inverse functions. So if you know how to graph y equals e to the x, you know how to graph the natural log of x. And this is actually, when I go to graph the natural log, this is actually what I think of when I do it. Okay, e to the x looks like this. That means log looks, okay. Because log is one that I have to stop and think about what I do when I sketch a graph of it. But yeah, that's what it goes. This one passes through the point 0, 1. This one passes through the point 1, 0. Inverse functions. Output of one is the input of the other. Output of one is the input of the other. That's one of the main things about inverse functions. Okay. The x coordinate of what x y coordinate, you swap the x y coordinates. So you can see why we have what I have down here. Since these two functions are inverses, we exponentiate a logarithmic function to solve for a variable in the argument, and we take the logarithm of exponential functions in order to solve for a variable in the power. That's why we do that, because they're inverse functions. One of them does the other. Learn them, know them, live them. You need to have those rules down pat. Okay, it's one of those ones. When we start taking derivatives of logarithms, those rules will make your life extremely easy. Okay, when we start working with logarithms in later on, particularly with differentials, if you can take a function that is one logarithm and split it into several smaller logarithms, those smaller ones are so much easier to work with that that's what you want to do. It truly makes your life much simpler. It really does. You need to know these rules. The log of two things multiplied is the log of the first plus the log of the second. Log of two things divided is the log of the first minus the log of the second. And the logarithms of something raised to a power is that power times the log of the base. You need to know those rules. And you need to remember, once again, they go both directions. They go both directions. Please take a minute to answer A, B, and C. Okay, so let's take a look at these. Move it up a little bit. So this one's fairly simple. Log of two things added is a log of the two. Is the log of something added plus the log of something is the log of the two things multiplied. This one here, log of 3x squared over x, which is the log of 3x. Being able to simplify these things, it's a big deal. It may not seem like it, but if you can rewrite things in a simpler form before you apply calculus to it, makes life a lot easier. And that's what this stuff is about. This one I need to split up. Log of 4x cubed minus the log of y. The log of 4 plus log of x cubed minus the log of y. The log of 4 plus 3 log x minus log of y. Not too bad, I hope. But once again, being able to do this is an important skill for later. This chapter is all about the basic skills you need to make your life easier later on. Okay. Questions? Okay. Using the rules we just worked on, solve for x. Okay, so my first step in this is to combine up all logarithms. If I have logarithms and non-logarithms, I need to combine up all my logarithms on one side and non-logarithms on the other side, and I need to combine all my logarithms into one logarithm. So my first step is to combine these up. So I get the natural log. Those of the natural log of 3x plus the natural log of 2 is the natural log of 3x times 2. So it's the natural log of 6x is equal to 5. Once I get one single logarithm, now I can exponentiate. Now I can do the exponent trick to it. You cannot do that while they are separate entities. You must combine them into one before you do that. Same as if you have multiple terms to e to the x, you need to combine all your e's to 1 before you can take the logarithm. So now, I raise both sides to the e power, and I get 6x equals e to the 5th, and I get x equals e to the 5th over 6. Once again, I want exact values. And do not take e to the 5th on your calculator unless it is a multiple choice test and your answer is in decimal form. Otherwise, leave it as exact values. The only other time you do not use exact values is if it's a word problem and that value does not make sense in exact terms. You do not tell your contractor that I need 4 pi cubic feet of concrete. You tell them, I need 12 cubic feet of concrete or cubic yards. But you understand what I'm saying? You use approximations when the answer makes terminally approximate, otherwise it's exact terms. Okay? We do exact values in here whenever possible. And that's it.